We now look into the chemical remnant magnetization. Here, consider a case that iron weathers and it moves through groundwater in a dissolved phase and then it precipitates elsewhere. And when it precipitates, usually in the form of hematite Fe2O3, and this hematite actually aligns with the existing magnetic field. If it was a reverse magnetic field, it acquires a reverse magnetic field. So, looking at the old rocks, we can understand if it underwent chemical remnant magnetization from this hematite, whether in the past in the earth had got normal or reverse magnetic field. But just with this data, we have no idea at what time it got deposited. For that, we may need the geochronologic technique or biostratigraphic information. Same thing with the detrital remnant magnetization and the thermal remnant magnetization. We know finally whether the rock is showing normal or reverse polarity, but we do not know at what time it got formed. So, for that again we need either geochronology or biostratigraphy. Same with the detrital remnant magnetization. So, in this case, what are the rocks we exclude in the chemical remnant magnetization? We have excluded the metamorphic rocks, we have excluded the igneous rocks. Since we are talking as precipitation, we are indicating the non-clastic sedimentary rocks. If a metamorphism happens on the igneous rock or the sedimentary rock, by increasing the temperature pressure, its degree of magnetization will be partly destroyed. Let us understand what is relaxation time. The magnetic ordering of grains eventually become randomized at any temperature. The duration is called relaxation time. Suppose there is a mineral grain and it has been magnetized. Now, if it is left like that at any temperature, slowly it will lose its magnetization, and the duration of losing magnetization is called the relaxation time. Let us understand qualitatively secondary magnetization. It is a viscous remnant magnetization, in short VRM. What happens here? Grains with relatively low relaxation time will tend to become remagnetized in the ambient weak field. What is the meaning of the term relatively low relaxation time? That means the mineral grain gets demagnetized very quickly. What is the meaning of relatively high relaxation time? That means the mineral grain, if just left as it is, will take very long time to get demagnetized. Interestingly, while we do not recognize turbidites and fleche formally as lithostratigraphic units, this VRM can be established for the turbidites and fleche. So, what is not formal in lithostratigraphy might find direct use in magnetic stratigraphy. Let us understand the meaning of the term isothermal remnant magnetization. It is a high field magnetization process and therefore, it does not generally occur in nature. That means, it generally occurs in the lab by human beings. But there are exceptional cases in nature. For example, lightning strike is one example where a high field magnetization can be induced. There are many details of what kind of minerals and rocks are useful in geomagnetic field studies or in paleomagnetic studies. One of the statements is that the shallow water carbonates are unreliable recorders of geomagnetic field, but then there are exceptions. Then there can be similar statements on red beds, fleche, molasse and turbidite. Now, we are going to see the magnetic elements. Consider a geographic north, not the magnetic north, and the opposite direction is the geographic south. Then from north, as you move clockwise, you get, after moving 90 degree, the geographic east, and 180 degree opposite to that is the geographic west. Vertically is the zenith and downward is the nadir. Z axis is defined in this way: vertical line, This geographic north direction is the x axis, and we take the y axis towards the east direction. This is east and this is my y axis. So, we have taken orthogonal coordinate system in 3D and we call this as the north east down coordinate system, and it is incorrect to say north east down. No, this is not the one. North is x axis, dash east, east is the y axis, and then down, down is the z axis. So, this north dash east dash down is like x dash y dash z coordinate system. Such coordinate system choice is common, and we also find such a choice of coordinate system in structural geology. Now, consider we have put a magnetic needle and the needle is presented as line F. This F line can be resolved along x, y and z axis. So, along z axis consider this distance is z itself. Along x axis it is x itself, and along y axis it is y itself. So, on the horizontal plane I can have a horizontal component h is the horizontal component, and obviously h is equal to square root of x square plus y square. D is the angle measured from north in a clockwise direction and is called the declination. D is measured from north in a clockwise direction and on horizontal plane, and this is known as the declination. Obviously, D is equal to tan inverse y divided by x. Now, we can define an inclination of f given by this angle, and obviously it will be equal to tan inverse z, this is the z, divided by h, this is the h. So, we can say f, the resultant, is equal to square root of z square plus h square, and we already know what is h. So, if I replace f is equal to this expression. Understanding about the magnetostratigraphic column. This one is a compilation from Proterozoic and it goes up to Cenozoic. First thing is that we do not have the good data set over here or a convincing data set. So, a question mark is given. It is difficult to establish the normal and reverse polarity zones clearly. This includes entire Proterozoic, entire Cambrian, not entire Ordovician, certainly mid Ordovician, and from upper Ordovician up to the beginning of Silurian, we have a clear idea that we have normal magnetic polarity. From this place up to middle Devonian and beyond, we are not sure what was the situation on the earth. Then this is a zone where a reverse polarity was established. In Carboniferous, a mixed signal was found, which is shown by these dashed lines, and beyond that there is a Permo-Carboniferous prominent reversed superchron from approximately 316 to 262 million year. Note that the numbers that I have given may change few million years here or there depending on the latest findings. This is also known as the Kieman reverse superchron. Kieman is a locality from where it was well understood. Then there is a late Permian Triassic Jurassic Cretaceous mixed signal, and after that as we move, a clear cut normal superchron was found, which is known as the Cretaceous normal superchron from around 83 million year to 124 million year. This was followed by Cretaceous Cenozoic mixed signal. I already said that the pre-Carboniferous information is not well known regarding magnetostratigraphy. So, this is pre-Carboniferous column where the data is less complete. the oceanic crusts are found from the mid Jurassic onward. So, here we have got good data set. So, we have got two supercrons here. We will explain the use of the word supercron. One is over here, the Permo-Carboniferous or the Kiaman reverse supercron, and the other one is the Cretaceous normal supercron. These are well established. For one of the supercrons we have used the word normal, and for the another supercron which is older we have used the word reversed. And as I said, normal will be represented by black box and the reverse will be represented by the white box or the white column. Now, the most basic unit in magnetostratigraphy called the polarity zone, and in geochronologic unit it is called as the chron. And what is the duration? Its duration will be 10 to the power 6 to 10 to the power 7 years. 10 to the power 6 means 1 million, 10 to the power 7 will mean 10 million. 1 to 10 million year is the duration. What is so typical about this magnetozone which are first to establish? Here either normal or reverse polarity should prevail. A magnetostratigraphic zone may consist of strata with a single polarity throughout, either normal or reverse. It can consist of intricate normal and reverse polarity unit NR. This kind of variation can also define a magnetostratigraphic zone, or dominantly either normal or dominantly reverse zones, but with minor subdivisions of opposite polarity. Take this example where it is a dominantly normal section, but there are a few thinner reverse polarity zones. So, this can be called as a magnetostratigraphic zone. Or consider there is a dominant reverse polarity zone, but there are a few thin bands of normal polarity zone. This can be considered as magnetostratigraphic zone. Several crons can be grouped into a supercron whose duration is 10 to the power 7 to 10 to the power 8 years. That means 10 million year to 100 million year, 10 to 100 million year, and several supercrons can be clubbed together as the polarity megazone, and in terms of the geochronologic unit, megacron is 10 to the power 8 to 10 to the power 9 years. A cron can be divided into smaller parts, the subcron, where events word is used, and the magnetostratigraphic polarity unit is called the polarity subzone. Its duration can be 10 to the power 5 to 10 to the power 6 years, which means it will be 0.1 to 1 million year. Polarity subzone can be divided into polarity cryptozones or cryptocron, where the duration can be less than 3 multiplied by 10 to the power 4 years. We discussed how the cron is defined. The question is how the crons are divided into subcron and cryptocron. The recommended hierarchy in magnetostratigraphic units and polarity cron is as follows. Here are the magnetostratigraphic polarity units. Here is the geochronologic time equivalent. Here is the chronostratigraphic equivalent, and here is the approximate duration. Polarity megazone can be compared with megacron, is comparable with megachronozone, and the duration is 10 to the power 8 to the power 9 years. Polarity supercron is comparable with supercron, is comparable with superchronozone, and is equivalent to 10 to the power 7 to 10 to the power 8 years. Polarity zone is equivalent to cron, is equivalent to chronozone, and it is 10 to the power 6 to 10 to the power 7 years. Polarity subzone can be compared to subcron, can be compared to subchronozone, and which is 10 to the power 5 to 10 to the power 6 years. Polarity microzone is comparable with microcron, is comparable with microchronozone, and is less than 10 to the power 5 years. Polarity cryptocron is equivalent to cryptocron, is equivalent to cryptochronozone, and its existence is uncertain. So, we may not be able to establish this one, may not be possible to establish everywhere. Just to recollect, 10 to the power 5 we say lakh in Indian and South Asian countries, 10 to the power 6 is million, 10 to the power 9 is billion. we find 10 to the power 5 involvement, 10 to the power 6 and 10 to the power 9 in the approximate duration. We can divide a magnetostratigraphic column or establish in a way that this represents normal and a part of it represents the reverse polarity. Now, although we say this is the normal polarity which should be completely black, using a red pen, so I am making it completely filled up by the red color, and we may call this as one chron, and in reality it may be seen in great detail as consisting of mostly normal, but a few reverse polarity. So, this can be a realistic high resolution appearance. In that case, we are able to divide a chron into several subchrons. What is event? Event is a short-lived polarity reversal of unknown duration, but what we are calling as unknown duration, with geochronologic techniques and biostratigraphic arguments, one may find out the duration also. What is the reason of these short duration polarity reversal? One can be excursions of the geomagnetic field, second paleo intensity variation, and third short duration polarity reversal. Basically, it goes to the same argument, short duration. So, we have got two possible reasons. The 4 crons were defined and they were deduced for Pliocene and Pleistocene by dating lava flows. So, the date was used, the absolute time was incorporated. We call it C sequence. Here we involve the paleomagnetic scientist names who were famous: Brunès, Matuyama, Gauss and Gilbert, to present this magnetostratigraphic column. Brunès varies from 0.73 million year, Matuyama from 2.48 million year up to 0.73 million year, Gauss from 3.40 million year up to 2.48 million year, and Gilbert from here up to 3.40 million year. These names were also used. When we say the C sequence, C stands for Cenozoic, but it is a very important point to note that the C sequence is not restricted to the Cenozoic only. From Cenozoic downwards it goes on and it reaches up to early Cretaceous. The numbering goes like this: C1, C2, C2a, etc., and it goes up to C34n. The C34n can be seen within the Cretaceous time scale and it ends over here. This is 126.3 million year, this is 125 million year, which means this is 126 million year and this is 125.5 million year, and the boundary goes like this. So, it is almost up to 126 million year, the end of C sequence. Since we write n for the normal polarity, therefore, C34n is shown by a black region, and where the C sequence ends, coming from top, right from C1, C2, C2, etc. up to C34n, where it ends, the M sequence starts and it goes down, which I will be discussing. And it starts with M0R, this is 0 not O, R for reverse polarity, and that is why it is shown as a white domain. Then comes M1, which is a normal polarity, that is why M1 is shown by a black domain. So, there is no break between the C sequence and the M sequence. While we talk about the Brunès, Matuyama, Gauss and Gilbert, note that there is no type section, there is no single section where these ranges have been established. However, the type locality of subchrons are known. The entire Brunès is not possible to demonstrate at any part of the earth, but information gathered in bits and pieces from several places of the world can lead to define the Brunès. For example, suppose at location 1, 2 and 3 we have records of Brunhes from here to here. So, we say type locality of subchron, then at type locality 2 from C to D, and in type locality 3 F to E. So, from these type localities one can establish the complete range of Brunhes from A to E. This is the meaning that the type localities of subchrons are known, but the type section for the Brunhes and the others are never established on the earth's surface. Even when the dipole field has a strong polarity, it undergoes swings in the typical amplitudes of 15 degree for 100 years to 10,000 years, and we call this as the geomagnetic secular variation. We have seen the word excursion earlier, what it means, more than 45 degree declination change. We have already defined the word declination, and I hope you can follow. If the declination changes to more than 45 degree or even a brief interval of opposite polarity for 3 to 6,000 years, KYR means kilo year, that means 10 cube years, or it means 1000. So, 3 to 6 K year means 3 to 6,000 years. And interestingly, at least 8 excursions have been identified for last 0.78 million years. We have less data in the pre-Jurassic rocks, we have strong data in the post-Jurassic rocks, and for the pre-Carboniferous rocks our data set is less, and naturally they are in the pre-Carboniferous rocks, that means rocks which are older than Carboniferous, we do not know clearly about the excursions, the durations. What is wiggle? This term also comes in magnetostratigraphy. This is revealed by magnetic anomalies from the fast spreading ridges. It shows changes in the paleomagnetic field. We come to this radiometrically based polarity time scale where Olduvai name is found. Let us understand. Olduvai normal polarity subchron. Olduvai is a location in East Africa. The Olduvai term you will also come when you study evolution of human, evolution of Homo sapiens. There in the Olduvai gorge we have found interesting fossils, and those are employed in studying evolution of Homo sapiens. The C sequence that we were discussing, C sequence were numbered from 1 to 34. Here 34 is oldest, 1 is youngest. So, in the succession C34 is at the bottom, C1 is at the top, and if you look at the magnetostratigraphic chart you will find after C15 we are getting C13, C14 is not present because in later studies C14 was deleted and overlap was found. Subsequently, many additional anomalies have been noted with complex letter symbols, number sequences were added up. So, not just C34, C33, C32 and then C1, there will be other complex ways of addition of anomalies. We will be explaining some of them. C27N.3, you may get such numbers within this C sequence. What does it mean? It means level or event is 30% up within normal polarity chron C27N. Here C is the C sequence, 27 is the number that you can find in this succession, and N indicates normal polarity. This C27N and within bracket 0.3, sometimes these brackets are excluded and it is written as C27N.3. This 0.3 is used in the sense of 30%. There can be another way of writing C27N30, and here 30 will mean straightway 30%. Let us look at C8N.2N. What does it mean? It means within the C sequence in C8 there is a normal polarity, and that normal polarity is broken into two parts. 2 indicates second oldest and N is the normal polarity. This is the meaning. So, it is basically a division of C8N. So, here the finer division is here and this one is a coarse division, or in other words C8N is the division and 2N is the subdivision. The Brunes will be represented by C1N. Here is the Brunes, this C1N. The Matsuyama will be given by C1R, here N for the normal polarity, R for the reverse polarity. Let us look at the Matsuyama. We find for the Matsuyama mostly it is white, So, we call this as C1R, R for the reverse. For Brunes it was N normal. You can see for Brunes it is all black, which means normal polarity. Now, if we write Jaramillo subchron, how it will be presented? C1R, within the Matsuyama a subdivision is made 1N. What is the meaning of 1 here? Here dot 1N will have same connotation what I have explained with C8N dot 2N. That means for 2N it was second oldest, so for 1N it will be the oldest normal polarity subchron, and this C1R dot 1N is called the Jaramillo subchron. Note that within C1R, that means which is the reverse polarity, there can be finer zones of normal polarity, and that one is presented over here. The cryptochrons are designated by dash 1 as the youngest and dash 2 by the next older. So, in the succession they have to be something, then dash 1 and then something dash 2. This dash 2 one has to be at the bottom, dash 1 has to be at the top, because this is the younging direction. And the youngest cryptochron is C1N dash 1. So, what does it mean C1N dash 1? Let us try to find out. This means in C1N, this is our C1N, the Brunes one, there can be several cryptochrons. The youngest one will be given by C1N dash 1. Coming back to Jaramillo subchron and the C8N dot 2N, what we understand, if I write C1R dot 1N, this is the oldest. Over that can write, if at all it is present, C1R dot 1S, and then over it I can write C1R 2N. So, in this succession what we get, this is the oldest, this one represents oldest and 2 represents the second oldest.